Let's look at the graphs of the photoelectric effect. Let's look at the graphs of the photoelectric effect, guys. From the definition that says energy is equal to Planck's constant times frequency, we know very well that the energy is directly proportional to the frequency. So if it's directly proportional, so it's going to be a straight line like that, right? And we know from this formula that says E is equal to HF, we can derive that. We say H, instead of F, we can say C over lambda. So we know there's an inverse relationship between the energy and the and the wavelength, and as well as there's an inverse relationship between the frequency and the wavelength, right? So our graph, it's going to be like this. That's the inverse proportionality between these two, and this is the graph that represents this. They're directly proportional. This one, they're inversely proportional, right? Now let's look at the graph of the kinetic energy. The kinetic energy and the frequency. So each and every metal has its own frequency, which is the threshold frequency. Let's say for this metal, this graph, it's going to be like that. Okay, let's say this metal, its threshold frequency, it's going to be there. So that is going to be the threshold frequency. So in this metal, if you are increasing the frequency of the metal, you are using a different light of the metal, you get a different kinetic energy. You're using a different energy. You increase the frequency, the kinetic energy will increase. I hope that makes sense. So there is a direct relationship there. If you're looking there, that's the best fit. So between frequency and the kinetic energy, there is a direct proportionality there, right? And in this graph, where your graph cuts in the x-axis there, in the y-axis there, that's the what? That's the work function, and it's a negative work function, right? And your gradient here, let's look at the gradient. The gradient, if we say change in kinetic energy, which is change in y over change in x, which is going to be what? The frequency. So it's the what? It's the Planck's constant, right? It's the Planck's constant. Why? Because the kinetic energy is equal to the energy minus the work function over h, which is going to be hf minus the hfo divided by that. So this simply means that it's going to be FFO divided by H, and that will cancel. So once you have a friction, a frequency minus the threshold frequency, that will be a Planck's constant. Guys, the gradient here is the Planck's constant, right? It's the Planck's constant. So what are we going to do about this? Now we can derive the formula from that formula that says energy is equal to the work function plus the EK max. So since our y-axis is the kinetic energy, so we'll make the kinetic energy as the as our y, which is the subject of the formula. So it's going to be E minus WO, right? So if we have that, we can arrange the energy as HF, and we leave the work function there. So if you see here, we have the EK max, that is our y, and we have the gradient, which is the m, and the x-axis, which is the x, and plus c, which is where our graph cuts. There is c. Our x-axis here, is the frequency. Here's the frequency. It's our x-axis there. I hope that makes sense. Now if we twist the two, we'll swap these two, so our graph, it's going to be a graph like that cuts there. So this is the what? Threshold frequency. So but if our graph continues there, it cuts where this is the energy, right? This is the energy, so our graph cuts there in the work function as well, right? It cuts in the work function. So if it cuts in the work function, that means our gradient, it's going to be 1 over, so it's going to be from this formula that says E is equal to W plus EK. So we'll make the friction as a subject of the formula, so we'll have HF there is equal to H, threshold frequency, times EK plus EK max, right? So we want F as a subject of the formula, so we'll divide everything by what? By Planck's constant. So we divide by Planck's constant, that and that is going to be F is equal to, and that cancel, you have the threshold frequency there, and then that means we're going to have 1 over H times the kinetic energy maximum, right? If you're looking here, this is your y, and this is where my graph cuts in the y-axis. It cuts at the threshold frequency. This is my c, and this is what? My gradient, it's m, and your k, that's your x-axis, that's your x there, that's your y mx plus c. I hope that makes sense, guys. Another graph, it's the kinetic energy and the wavelength. They are inversely proportional. So the graph, it's gonna be like this, and then it's gonna be a curve that shows the inverse proportionality, and then that means where this line, it means what? It's the threshold work function, or it's the cutoff work function. So this side, it's where the work function is lesser, not the work function, the wavelength is lesser than the threshold the threshold wavelength. And this side, which is here, the photoelectric effect, which is the emission, has occurred, the photoelectric effect. So in this side is when the wavelength of the light is greater than the threshold wavelength. So here, no emission. So what do I mean by no emission? That means no photoelectric effect. Even here, guys, even here in this graph, where there's a work function here, okay, here in this graph, guys, this one, so we'll have a line here. So here it is when the frequency of the light is lesser than the threshold frequency. That means here no emission, which means no photoelectric effect, right? So here above this, so that means the frequency of the light is greater here, is greater than the threshold frequency. That means emission occurred here, which means the ejection of electrons occurred there. Very important. Let's look at another graph. Another graph here, it's the current and the intensity. The current and the intensity, guys, they are directly proportional as well. The current and the intensity. The greater the intensity of light, the greater the current, right? Even here, the greater the intensity of light, the greater the number of electrons. The number of electrons ejected per unit time, which is the current. The graph will be like that, right? And there's another graph, guys, here. This graph, it shows it's a graph of the kinetic energy and the work function. Graph of the kinetic energy and the work function. Kinetic energy maximum, and it's in joules, and the work function, right? The work function, which is going to be just an energy, the energy of the energy of the light. So the greater the energy, the greater the kinetic energy. So the graph, it will be like that. So that means here is the what? Is the work function. So if we draw a line here, this is when the energy of the light, has a lesser energy than the work function, which is the photoelectric effect has not taken place, no emission here, right? And here above this threshold frequency, that means the energy of the light is greater than the what? The work function. That means emission of electrons has occurred there, which is the photoelectric effect, right? Now let's look at this popular graph now. This popular graph where we have the kinetic energy and measured in joules, and let's say here we have frequency in hertz, right? So let's say we have different graphs like this. This is let me use another colored pen. Let's say we have another metal here, another metal here. So here, which metal has a greater work function? So the one that has a greater work function, it's this one. So this is the work function, it's negative, and this one, its work function is going to be there. So it's going to be a negative work function, and this one, its work function, and this one, its work function, it's going to be there, which is it's a negative work function, right? So let's say it's a metal A, B, C, right? If you look at the metal A has a bigger work function than B and C, right? Even the threshold frequency, they have a different threshold frequencies there. So this is the threshold frequency for that, threshold frequency for that metal, right? I hope that makes sense, guys.